So basically what this does, this is nothing but a calculator. It's a calculator, however, that allows us to compile math, and it allows us to see the assembly code that a computer runs when it's performing math operations. So let's do something simple. Add 1 plus 1 and hit equals. Any surprises there? Right, we got 2. Makes sense. Why is, or how does our computer actually get 2? Can anyone name the circuit that's doing that computation? Yeah, an adder, right? So we're using that adder circuit, we're sending in a 1, and we get 2. But what does the assembly look like for that? Because there's a lot of wrapping for that adder circuit that'll allow it to run along with the operating system and the program and everything else doing it. And to do that, hit this little down arrow beside the equal sign. Go compile to assembly and target Win32 and hit that. So what you should see there is the assembly code that runs it, right? A couple things to point out about that. These dots basically is a special directive. It tells it, .386 tells it what version of assembly we're using. And same with the model small, and include lib says we're going to want to use the Windows code to print a value, because printing a value is a complicated thing to do. We don't want to rewrite that. This PF is a string, and that string consists of just a % and D, and that's what we use to tell Windows print a decimal number. 0AH, so this is a slightly different notation. H at the end is what Windows uses for hexadecimal, so what is 0A in decimal? 10, right. So, because A comes after 9, and then 0, we stick a 0 at the end of the string to tell it that that string is done. So now we actually get into the interesting stuff. So we push 1 to the stack. 1's on the stack. Set EAX to 1 and pop 1 out of the stack into EBX. Right? You can all kind of follow along in the code you see there. And then we run the add command. That adds EAX to EBX. And in this case, times 86, what your computers are running, it takes the first value to be the one it stores in. So it's going to store that value in EAX. Push EAX. This pushes that to the stack. And then we're going to LEA's load effective address. It sets the address of EBX to be, or it sets EBX to the address of that string. It then pushes that. So we now have the string, we have the value, and we call printf. Printf is a Windows function that will go and print that value that we've just calculated, which is 2, using that string. So it prints 2 as a decimal, then a new line, and then finishes. Okay? And then again, we push 0 and call exit. So 0, the exit function, Windows is going to get that. It's going to say, OK, we're done. Any questions? Yes?
Why do you push 0 right before you end?
Good question. So when we exit a program, we usually have a return value of that program to tell the operating system what happened. 0 is the universal one for it worked, it's good, we're done. If we push 1 or any other value, that's an error code. So it says something went wrong. This is the error code. Sorry, remind me your name?
Alex.
Alex. Yes. And Edwin.
Yeah.
Yes.
Can you repeat again what LEA does?
LEA stands for load effective address. So what we'll notice up here is .data. So actually this is slightly different than some versions. Sometimes you'll have a label up here in other types of assembly, and it's going to have, in that main memory that we saw in our CPU, it's going to contain the string value of this. So there's a binary value that represents %, binary value that represents D, AH, or 0A, is a new line, so 0A is the binary value in hexadecimal representation that represents a new line, and 0 is just 0 in every number system. So that is going to be taken up in a chunk of the memory, and PF is the identifier that says that is, or that points to which location in memory, right, that we're sticking into that multiplexer to get the memory from, contains this string. Okay, seeing a couple nodding heads. Any questions? So that's PF, points to that. LEA loads the effective address of PF, sets EBX to that value. So we can then push EBX, because we can't push a constant. Other questions? So what we'll do now is we'll actually run this program, because we can do that. So hit the down arrow again. This time we're going to compile to executable, and again target Win32. So you should see something like this. Anyone seeing anything different? Oh my goodness, something's going wrong. Oh, you know what's happening. Okay, none of these machines actually have the assembler installed. So that's okay. This part you can see up here, you don't miss anything. Yeah, we do need a piece of software that knows how to take this assembly code and convert it to machine code. My machine has it, yours don't. So that's why it isn't working on yours. I forgot to tell them to put it on. What this is doing behind the scenes is it is running that assembler, and it assembles this code and runs it and gets 2. So I can, given the time, I won't do it now. I can give you that assembler for later on so you can try it out yourselves. But just to show you, I'm going to open up the Windows command line, and I'm going to change directory. So CD stands for change directory. And we change the working directory to %temp%. That %temp% is a Windows variable, and that variable is our temp directory, which is where the assembler put our exe file. I'm now going to dir star.exe that lists all executables in it, and we'll see that we have this out.exe right here. Am I like standing in the way of the projector? Just realized that, sorry. So we have this out.exe right here. That is what we just compiled. So we can run that. So we're going to type out.exe, and it runs that executable program and gets 2. So that is at the very basic level. We take our math, we compile it to assembly, we assemble it to an executable. That's this machine code that we just looked at. It runs on our processor, which is a CPU made out of registers, multiplexers that we looked at, and it calculates 2. It's kind of a lot to take in. Is it all adding up? You guys kind of understand now how these mystic transistors in silicon could calculate 2? It can do more interesting things. So what I'll get you to do is try, say, making a more interesting expression. So adding brackets around it, adding some multiplication, you know, doing something like that. A lot of this, like, unfortunately, this program cannot compile partial differentials to assembly, so don't try. But basic math it can do, and then compile that to assembly and take a look at what it does. Right, so you can see it makes more extensive use of the stack. We now push 5 and 1. The reason for this is that this 5 we have to handle at the very end. So we're going to leave that on there for the rest. And then we push 1, add the 1. We get 2, push that to the stack. Then we have 5 and 2. And then we can call the command to multiply those. So we can use the stack to do our order of operations. And that's the main reason the stack actually exists. So why don't you guys go ahead and try something like that. You can do something really complicated, like adding a bunch of different values, except don't make a syntax error, and see how it handles the stack for that. Anyone have any questions on what you're seeing? Trying to understand what's happening on this stack? Yes.
What's this part again? So I get the whole push, move,
Yep.
pop, yeah, and once we get to MUL.
Oh, so mul? Yeah, good question. So mul, MUL, is the multiply command.
Oh, right.
So in this case, it only takes one argument. That's because times 86 is lazy, doesn't want to do all that multiplexing. So mul takes EBX and always uses EAX. Always, yeah. And always stores to EAX as well. Anyone have any other questions on what you're seeing in the assembly? What the stack's doing? Oh yeah, so LEA is load effective address. So it takes PF, that's this string here, loads its address into EBX so we can push that address, and that'll give printf the function that, or the string that says print a decimal, then a new line, then we're done.
Yeah, so what does EAX and EBX stand for?
Okay, so those are just registers. Yeah, so it's like AX and BX that we were using before. The E means it's 32-bit.
Okay.
So extended AX. Yeah. The value in EAX should be 2, right? Or whatever value we just calculated. That's now in the stack. And then EBX, which we also push to the stack, is the value of that string. So printf so it pops the value of that string and says we need a decimal, then a new line, then end. It then pops the next value from the stack, which is the value we just calculated. So it prints that value, then the new line, then the end. Yeah, so we push it because it's going to get popped by printf. Yeah. Yeah.
When we're adding, it's both. It says both EAX and EBX, but when we're dividing or multiplying, it just says.
Good question. I'll say that to the class because that is a good question. Sorry, what's your name again? Sarah, right. So everyone, Sarah just asked a good question. She pointed out that adding and subtracting is 2 registers, multiplying, dividing is just 1. The reason for that is Intel times 86 is lazy. It doesn't want to do all that multiplexing. So we multiply and divide. We always use EAX as one of them. So it's going to take the other one we give, multiply or divide it by EAX, store the value in EAX. So it's using EAX. So a couple hands, yeah. Okay, so I think most people have kind of figured it out, so we'll move along. If you have any questions afterwards, you can feel free to talk to me after. So getting back to this, one thing we'll look at is a little bit more complicated of an evaluation, and that is evaluating a sum. So I can get rid of that. What you'll enter is what you see on the screen right up there. To do that, get rid of this, we can use the sigma button. So press this sigma button. Sigma stands for sum. And we can say set n from 1 to 100. So 1 to 100. And then we'll put n. So that's just going to sum up all the different values of n between 1 and 100. And I'm going to stick this @reg at the end. And that just tells us to store the n in a register, which makes it a lot faster, because registers are hardwired to the CPU, main memory is not. So first just hit equals, see what it gives you. So I think most people are on 50-50. So we'll take a look at how it's getting to that. So again, we'll look at the assembly. So we're going to target, we can do Win32 again. And we have a bit of a looping structure here, because a sum is a loop. Am I in the way? Kind of. Okay. So now we're using a bunch of different registers. We're using DI. That's our destination index. That's our 100. That's where we're going to finish. XOR, DX with DX. When we XOR anything with itself, we get 0. Because if they're both 0 or both 1, we get 0. So that's a fast way of setting it to 0. So DX is now 0. And then we set CX to 1. So CX is our counter. So we start at 1 because it's our initial value, right? And we're going to decrement CX. That's just to set it properly. And then we're going to increment it again because we want to increment it every time. Notice this SRT, it's short for start. That's a label, right? So we're going to start increment ECX. And that's going to count up by 1 each time, okay? Now we're going to do our actual calculation. And our calculation isn't much, it's just n. So our n is ECX, and we're going to add it to EDX. EDX, which we set to 0 with that XOR, is our sum. Right? So we start out, we add 1 to that, then we add 2, then we add 3. We add it each time. The next thing we're going to do is compare. So we compare ECX to EDI. CX is our counter, DI is our destination index. So if they're equal, then we're going to continue. If they're not equal, we're going to jump not equal up to this start label. And then when we jump, we increment again. We set BX to CX again, and we're going to add DX to BX. So that's going to add the value and compare, is it 100 yet? If it's not, we're going to repeat. If it is, we move on. And at the end, we just print the value as usual. And so we can go ahead and compile this to an executable. It'll run, and that'll print 50/50. So that's running that assembly code in a looping structure, right? So back, 200 years ago, if you wanted to add 1 to 100 and you didn't use any mathematical tricks, that would have taken a long time. Now it took a couple nanoseconds, right? So looping structures are really what makes computers so powerful.